Hello. Hope you're staying safe in this quarantine, and we're going to continue working on a number of problems here. Today we're going to be looking at the application of rational expressions. So the application of rational expressions is going to cover a number of different areas. The first area that we're going to look at, we're going to find the value of an unknown variable in a formula. The second part, we're going to solve a formula for a specified variable. Third, we're going to solve application using proportions. Fourth, we're going to solve application about distance, rate, and time. And last but not least, we're going to solve application related to work, our work rates. Now, one of the things here is that number 5 is going to be one of the most popular application of rational expressions. Most exams generally have a lot of problems relating to number 5. But any of these can be a section where they have a problem relating specifically to that specific sections that we're going to be working on. So to get things started, let's get things started off pretty nicely right here. We're going to be looking at this nice example. If we have the current and we have the total resistor in electronics, very, very popular application right here. This is 4.5 we're working on. The formula for calculating the total resistance of R of a parallel resistor R1 and R2 is given by the formula as follows. Now, we don't even need to know none of this fancy stuff, but this is a place where this is applied a lot. It's given as follows. Now, what we want to do, we want to find R1 if R is 15 ohms and R2 is 20 ohms. Now for this simple problem, all we simply need to do is plug in for R and we're going to plug in for R2. And then from there, we can solve accordingly. So this is very consistent with what we have been doing before. If we solve, put whatever we have in the formula as usual. Once we put whatever we have in the formula, what we're going to do, which is pretty simple here, is multiply throughout by the LCM. Now it's pretty obvious to see that the LCM of 20 R1 and 15 going to simply be 60 R1. If we do 60 R1, what we simply do, we multiply throughout everything by the LCM. Once we multiply throughout everything by the LCM, the result would be as follows on the left and the right. Now, an alternative way to do this problem would be to just simply multiply the top and the bottom by what is different. So we could do that if we choose to work through accordingly. If you recognize that the LCM of 15 R1 and 20 would be 60 R1, what I could have done is incorporate, this would be 50 times, we need this to be 60, so this is going to be times 4 times R1, just to make that right here. Good. And then we would have to multiply the top by the same thing. So this is going to be 4 times R1. And that would be, for the right now, same thing. We will have 1 over R1. We could multiply this by 60, multiply that by 60. And if we do that, plus 1 over 20, we could multiply this by 3 R1 and multiply this by 3 R1. Now we could do it like this and then write the common base. Either way is correct. It's just a matter of preference in terms of how you're going to be doing it. Now looking at this problem, it makes significantly more sense to actually just work through it as is because of how the fraction is written here. And then we're going to simply simplify with a different situation right here. So to simplify, obviously, we're going to have 15 into 60 R1, going to simply be 4 R1. Right here, we have R1 into R1, that's simply going to be 60. And then 20 into R1, that's simply going to be 3 R1. So we could have done it like this. Now, solving for R1, obviously, we're bringing 3R1 to the left, so bringing this over to the left, the result going to be R1 equal to 20, and that solves this particular problem. All right, so let's keep it going with this problem. So that's another, we're going to look now at another application. So we're going to look at ratios, and I want to be very, very clear. with ratios, because this is one of the sections that is super important in terms of working out a lot of problems. So real quick, a certain chainsaw requires that the gasoline be mixed in oil in the ratio of 32:1. Now, in the stock market, winning stocks might outnumber losing stocks in the ratio of 7:3, and the ratio of A to B may be written any of the following ways. So just be familiar with this. A to B, this is A to B. The next one, we have A using this right here, that is still A to B. We'll read that. And A divided by B still mean the same thing. So just to back up a bit, just be very familiar with all three, because these are the different ways that this can be represented. So if we look at that now, we keep it going. So a proportion is a statement that two ratios are equal. Very easy, very simple concept, but we need to be very familiar with that. So an example here, we have 1/2, and we got 4/8. Now we got 3 supervisors, 25 workers, 12 supervisors, 10 workers. So notice right there, if I simplify or reduce these, this gives me the same fraction. Obviously 4 into 4, that's 1, 4 into 8, that's 2, so that's going to be 1/2. So again, we have A over B. I'm just writing this arbitrarily. A over B is equal to C over D. Those are proportional. So proportions are useful, an important type of rational equation. Very, very important. Now let's take this simple example. A toy model indicates on the box that 1 inch on the model is equivalent to 8 inches on the actual automobile. How long will the model be if the actual automobile is 15.7 feet? Now notice the model is given in terms of inches. So what I'm going to do is to convert the 15.75 feet to inches before I even start to do that problem. So looking at this problem, if I call the length of the car X, what we're going to have is, this is the unknown right here, and this is what we're trying to find. Now, the thing is, if I call the actual automobile, the actual automobile is 15.75 feet, convert that to inches would be simply multiplying that by 12, and I'm going to get 189. Now to find the actual length of the car, I'm going to use the ratio as follows. So if I know that the actual length was 189, what I'm simply going to do, I can use the ratio that was given. It is 1:8, and I know if this is 1:8, whatever the car be, it's going to be x to 189 to get that ratio. So doing that, I'm formulate my equation. Very simple. 1:18, that's the ratio, and the car I know is going to be x to 189. I can simply cross multiply, right? Or what I could have done in this case is just multiplying by the LCM. Now some books say LCM, some books say LCD, which is 3402. We can do either such. Now if you opt to cross multiply, again, this is another way we could do that. The result here would have 189 equal to 18x, and then we could simply solve for x, and that would yield the same results. So notice if you divide that by that, you're going to get x equal to 10.5. Very importantly right here, that we get the same result if we actually divide that by that. Now again, you can multiply through by the LCD. You also could say, well, just be careful here, LCD is the same thing as LCM, or we simply could equalize the denominators. It doesn't matter. However, we have approached this problem that can be used to solve the problem. So keeping it going, so if the actual automobile is 15.7 feet long or 189 inches, the length of the model will be about 10.5 inches. All right, now this is another important application that I want to hit. Solve a proportion problem involving rates. So this is a very nice question. Again, very popular. Alicia spent 5 hours studying for her last accounting exam and got 60%. She has already studied 2 hours for her upcoming exam and would like to get 90% on the exam. If we assume that Alicia continues to increase her score at the same rate as before, how much should she study to get the 90%? Okay, so she already studied, spent 5 hours for the last exam and she got 60. She already studied for 2 hours and she's desirous of getting a 90%. Now again, this is simply a proportion problem and we're just going to set the proportions up pretty easily. So by looking at this, we want to figure out how much you need to study to get the 90%. Now we already know real quick that she studied 5 hours and got 60. So if she already studied 2 hours, all we need to know is that the X here going to represent the additional amount of hours that she need to study to actually get the 90%. Now, one of the challenge with this problem is to figure out how to set it up. Once you understand how to set up this problem, you realize that it's work out to be very easy. So just note the proportion, 5 hours, 60%. So those go together. We already spent 2 hours. We want to figure out now what will go with 90% of the exam. So we already spent 2 hours. We just need to add that additional time that we need to spend to study to get the 90%. Now once we reach here, we can then simply solve. We have multiple ways to solve this. We could cross multiply by just simply multiplying 90 by 5 equal to 60 times 2 plus x, or I could just simplify the LCD and multiply through by the LCD. Now if I solve that, just want to show you real quick. Here again, I'm multiplying by the LCD. It still would yield the same result. So if I did that, it works out as follows. And then I solve, I'm going to get 5.5 for x. Now, very straightforward. If I multiply through by the LCD, notice right here when I simplify 5,400 divided by 60 times 5, going to give me 90.5. 90 into 5,400 going to give me 60. Now again, this is not necessary if you don't want to do it like that. What you simply could have done is just multiply by 90 times 5 equal to 60 times 2 plus x, and then once you solve, you're going to get this part of the equation right here. So you could have done that instead and then solve, and the result would be the same. So another way to do it is find the LCM, equalize the bottom. You have multiple ways to do it. It depends on your preference. All right. So to get the 90%, 5.5 hours, not bad for 90%. Some people have to study significantly longer than that to get the 90%. So let's keep it going. Now, this now is another awesome problem. This is a problem that is one of the most difficult for a lot of students. So let's spend some time to go through this carefully. The current of a river is 3 miles per hour. It takes a motorboat a total of 3 hours to travel 12 miles upstream. So we're going upstream. So this is my little boat. If I may draw this, I hope you don't think my drawing is crappy, but I still got some drawing skills. All right. So this is my little boat. So I'm going upstream. Good. And it takes me 12 miles to go upstream and 12 miles to return. So 12 miles to go upstream and 12 miles to return. So this is 12 miles. Good. That way, and 12 miles that way. So we wonder, what is the speed of the boat in still water? All right. So the current of the river is 3 miles per hour. So if the current of the river is 3 miles per hour, let's just put this right down right here. We know the current is 3 miles per hour. So since it's x is the speed of the boat in still water, we know that upstream we are going against the tide. So going against the tide, we're simply going to be subtracting 3 from x. Because if x is representing the speed of the boat, I know that it's going to get some resistance with the water once it's going upstream. Now, if x minus 3 represent the idea of going upstream, going against a current, obviously going coming back down, we're going to have the current pushing us ahead. So coming down, the current going to be x plus 3. So that is the hardest part of this problem here, to figure out the x minus 3 and the x plus 3. So once we figure that out, life becomes kind of pretty easy now. So we can formulate our equations. Now we need to be very, very mindful of this formula right here, which we want to hit. This is time is equal to the distance over the rate, right? And that makes perfect sense, because how fast I'm traveling is dependent on the distance covered over a particular time, or the rate or the time going to be the distance over the specific rate. It's very important there that we kind of understand that. Now, I love to write it like that. I like to say speed. I like to write it speed equal to the distance over the time. I like to write it like that. This is another way to write it. But the rate is the same thing like the speed. So I want to be very careful with that to make sure you understand what I'm saying. So if I switch this position right here, notice that d still would be d over s if I rewrite, right? Because if I multiply t by s, that's st equal to d. So as a result, I realize that t is going to be d over s. So this is the distance, that is the speed. So the speed is the distance divided by the time. It's more natural to think about it like that, because how fast I'm going, right, is determined by the ground that I'm covering over a particular time. That is why when you're in the car, it's a miles per hour, which means the amount of miles I'm covering, the distance that I'm covering over a particular time. All right, so let's run through that now. So it is always nice to have a little table right here. And to write a little table right here, it makes sense because it makes life significantly easier. So notice is the rate upstream, this is the rate downstream with the current. And we know that the total distance is going to be 12. Now, again, the formula is t equal to the distance over the rate. And that makes sense because that will represent my time over a particular period. So the formula then that arises right here, we're going to have the time, which is going to work out to be 12 over x minus 3, because this is representing my rate. I'm going upstream, and then coming downstream, it's going to be x plus 3 over 12. With that being our case, we note that the total time is 3 hours, because that was given in the problem. If we back up, right, the current of the river is 3 miles. It takes about 3 hours to travel upstream and return 12 miles downstream. So that's a total time covered. So the total time here is going to be 3 hours going upstream and downstream. So we want to make sure that we're aware of that. Then we simply need to add both of these. Now to add both of these, it's very easy now. This is where the algebra comes in. We got two ways to do it. What we could do is multiply this by the difference, x plus 3. X plus 3. Could multiply this by x minus 3. X minus 3. Could multiply this, the denominator right here, by x minus 3. X plus 3. X minus 3. X plus 3. Now the algebra becomes very, very easy from here on, because once the bottoms are the same, we can drop the bottom and we're only going to have the top. So notice right here, if I go forward, we have that as the LCD, which is the same thing, and the result going to yield that. Now again, I want to make it very clear. If I got 12 over x minus 3 plus 12 over x plus 3 equal to just 3. If I multiply this by x plus 3, x plus 3. If I multiply this by x plus 3, sorry, not x plus 3 right there, x minus 3 right there, right? Because this is x plus 3, so I need x minus 3 right here to make it be the same. And then this is x plus 3, x minus 3, x plus 3, x minus 3. Now the denominators are all the same to equalize the fractions. This is simply going to be 12x plus 3 plus 12 times x minus 3 equal to 3. Now this is the difference of 2 squares, so that's x squared minus 9. So that is how I arrive at that. Now alternatively, you can do it however you want. I don't really care how you do it as long as you get it right. And that's going to be the important thing right here. So working this out, we arrive at that for the expansion. 3 times that going to be 3x squared. 3 times that is negative 27. And now my goal is to get everything on one side and solve for x. So that is my fraction. Divide everything by 3. I got x squared minus 8x minus 9. So factoring that, we're going to get x equal to 9 and x equal to negative 1. So the speed of the motorboat in still water is going to be 9 miles per hour, because obviously we can't have a negative speed there for that particular problem. So that is that for that application problem. Pretty easy, right? Once you understand the basic and once you can actually work through those problems. All right. So this relates to work done. And this is a very, very popular area that a lot of problems always come from. There's a people work at different rates. If the letters R, T, and A represent the rate at which the work is done, the time required, and the amount of work accomplished respectively, then the amount of work that is done is equal to the rate times the time. Now notice this is parallel to saying distance equal to the R times T, right? So just be aware of that. So the amount of work can be measured in terms of jobs accomplished. Thus, if one job is completed, A is equal to 1, and as a result, R then going to be 1 over T. Now, this is the single most important rule that we need to have right there, because that's going to help us to do almost every question that we're going to be working on. Notice again, if this represents the one job done, and we have two people normally working together to complete one job, the rate always going to be 1 over the amount of time spent by that person. So just be mindful of that. So let's look at this problem. They say an inlet pipe can fill a backyard pool in 10 hours. So straight off the bat, I know the rate here going to be 1 over 10, right? While the drain can empty it in 12 hours, right? So this is emptying it. Now again, because this rate here is going to be, this is 1 over 10. We know here we're trying to empty this. So if we're put this amount of water in it and we're trying to empty it, this must be represented as negative. So that's going to be negative 1 over 12. If both of the inlet pipe drain are open, how long will it take to fill the pool? All right. So just be aware of that. How long will it take to fill the pool? All right. So if we're coming in 10 hours right there, going out 12 hours to enter the pool right there, obviously we have the formula right here. It's going to be 1 over T for the job per unit of time. That's all we need to remember. Just remember that whatever job that you get when two people are working together and we need to figure out the rate, all we simply need to do is have 1 divided by T, which is going to be the time that is under consideration. So let X represents the time it takes to fill the pool. Obviously, it's going to be 1 over 10, and to empty the pool is going to be negative 1 over 12. Now, looking at that real quick, the time they take to work together. So the time they take to work together, normally going to be the unknown that is there. So I'm multiplying it by X, have the rate, that is my time. So this is the time that they're working together. This is the unit of time that they're working together, which is the same. It's going to be the same amount of time to complete that specific job. So adding both of those normally going to give me 1 job done. And this is the common way that this problem going to be done in all situations, right? So 1 job done here, which is my 1, and then X there is my common time. Good. And then this right here gonna be my rate. So just want to remember that. Good. So with that being the case, all we simply do now is solve. Again, I could find the LCM, or I could just simply multiply throughout by the comma, the top and the bottom, but it doesn't matter how you do it once you're able to solve effectively. So that arrives at x equal to 60. So it takes 60 hours to fill the pool if both the inlet drain and pipes are both left open. And that's it. That is it. That is all the application problems that you're going to do. All right, guys, have a phenomenal day. Keep working hard and make sure that you enjoy some mathematics.